Some learning on a Saturday morning might be challenging, maybe not for you, for me. For you also? Yeah, okay. So let's take it one step at a time. So, yeah, let's just make a brief summary what we covered yesterday. So, yesterday we went to the IPR first of undersaturated oil. We cannot assume anymore that is ideal. And remember, if it's ideal, we are assuming that the product of these two guys, the viscosity and the BO, is a constant. Okay. Now we don't assume that anymore, but I told you that it changed like a straight line. And then if we evaluate this product at an average pressure, well, we can use basically the same equation, okay, as before. A linear coefficient times the difference in pressure, and and this coefficient, because the average pressure is changing, okay, the reservoir and PWF are maybe changing, so you have to update every time these two change. But no big deal. Now with gas, we did exactly the same development, but now the issue was that when we get this integral of properties, it's not so simple. How do we handle that? Okay, so I told you if we plot these properties, how they change with pressure, you find two very distinct regions, and that we took from the book of Mike, okay, from Golan. You have a region where you have a straight line. That means it's just a constant, okay? P divided by that, if it's a straight line, that means that this is a constant, okay? Then I have a region where it's curved, non-linear, and here we don't know, okay? And we have another region where it's fairly constant. So in that, again, this is a constant, all of that, so that makes my life simpler. So for low pressure, first, I think that's the first thing we have done. For low pressure, okay, we evaluated μc at any pressure, okay, so it can be at the bottom hole, can be at the reservoir, at any pressure, but then the integral gave you p squared minus p squared. And this equation, I told you, looks very similar to the back pressure equation we have used on day 2, okay, that was measured on the field. Okay, it was measured by test. And the main difference is the n. And if you know, we mentioned that n is between 0.5 and 1. 1 if it's Darcy, 0.5 if it's turbulent. And in this case, we are assuming for our derivation, we are departing from the Darcy expression, Darcy law expression. So it makes sense that for our case, n equal 1. Then for high pressure, which is again the easiest case, so we said that we evaluate all of that at one pressure. It doesn't matter. So I chose reservoir pressure. You could have chosen any pressure here. And you get a very similar, it's like a liquid IPR, okay? Which is also nice. Gas for high pressures, and we are saying here high pressures is more than 275 bar. It behaves like a liquid, which is very convenient. Now for the medium, I have to make this integral. Okay. But as this pressure will change in the field, you will not be operating usually at a constant PWF. So it becomes very non-practical to make the integral every time we evaluate this function. So the way we do it, we define an M function, which is an integral from a reference pressure, which in that case is surface conditions, all the way here is the area under the curve, and then we subtract another integral from to the lower bound of the integral. Okay, so you have the difference. The integral from PWF to PR will be the difference of these two M functions. And the M function is something that you can ask from the lab to generate for you. Or you can ask from your PVT expert, you say, generate this M function. It generates a table. And then I have this reservoir pressure, I use this M. And I have this bottom hole pressure, I have this M. And I make the difference. And that gives me the integral between PWF and PR. A very clever way to deal with, with this integral. And this equation, in principle, I should apply it to this curved region, nonlinear. But I can really use it for any region. Okay, I'm not making any assumptions, so I can use it for here or here or here. Remember, if I'm in the low pressure region, both pressures, bottom hole pressure and reservoir pressure, have to be here, both. If I'm using M, doesn't matter. I can use it in any region. And if I'm using this high pressure expression, okay, the one that is very linear, I have both my pressures have to be here in that range. Both pressures. Then you did an exercise and we compare both. Okay, we are making it in like a bit in the high pressure, but really is the medium pressure range. And we saw there is a significant deviation if you use the M or if you use the squared. Okay, the squared is actually much more conservative. If you make your design of your well based on this one, okay, and then you get this one, it's a nice surprise. But if you do the opposite, it might be that your project is non-economical. Okay, you say, well, it's not worth to drill this well, but in reality, you could have gotten a very good production. I did a test. I also told you if you wanted to try that. I say when we are below 100 bar or 80 bar, both curves are the same, no matter if I use the low pressure or the M, okay, because they should come close. Now we came to the choke. I told you it's very demanding equipment. From the field is one of the most that experience the most wear in the field. And there are two types. One of them which is fixed opening, called positive choke or beam choke, in which I have an insert that I change the diameter. And the diameter, it goes in increments of 1/64 of an inch, and typically from 1/8 to 2 inch. But if I want to regulate my flow, let's say reservoir pressure goes down, and then I want to keep the same rate, I have to stop the well, open here, change the insert, and then put the well back in production. Or I might have a choke battery where I'm working on one, and then while the other is being changed. The adjustable choke, usually they are more expensive. So only if the rate of the well allows, I can install it, or for subsea wells or platform wells, they typically have an adjustable choke because these are expensive wells. So I don't want to be stopping production every time. Two types, this rotary disc that is very well known, very much used. There are many places where they still use it. Here you have a picture. And cage, this is very popular, more expensive, but it's what almost every subsea system are using, okay? Cage type choke. There are many issues on a choke, principally erosion. Here we made an example. How is the expansion of the choke, which is, according to thermodynamics, is isenthalpic. And we're going to use part of this expansion today, okay? Then we said that the choke delta P versus Q, remember we're always looking either at the available pressure, either our discharge pressure versus rate. Okay, that's the curves that we are looking at. So it does something like that in the subcritical regime, and then at some point I reach critical flow at the throat, okay, where the velocity of the fluid gets equal to the sound velocity in the gas. that means that any change that happens here, it won't be propagated up. Okay? That means that it doesn't matter how I lower this pressure. Let's say I put a compressor or a vacuum and it's trying to get more rate, I won't be able to do it, because just simply that pressure change doesn't see at all any pressure change. Okay, so that's what we call the critical regime, and I told you it happens usually when P2 divided by P1 is 0.55, or you can use that expression where K, be careful, is not permeability, but it's Cp over Cv, this gamma, the ratio of okay. Then we did an experiment. How does it change with diameter? And we said, well, the critical point doesn't change. Okay. What is going to change is at which rate do you reach that critical point. If you have a smaller diameter, well, you're going to reach that delta P at the lower Q. Okay. Then came this, which was a bit controversial, and so what if I change the inlet pressure to the choke, how the curve looks like? And I gave you some justification why it should look like the curve to the right if the pressure is increased. But we are going to come back to that today. And finally, we derived the choke equation for liquid. And I told you, we normally don't use choke for pure liquid, because either if it's an oil well, you have that gas will be liberated already at the wellhead. Okay, you don't have normally just pure oil. You have two phases, or you have gas. Okay, so this is not so, but it's interesting to see how the model is derived. Okay, how almost every choke model is derived. And it's derived by, you say, 1 point upstream, 1, and then 1 point downstream at the throat. Okay, and you apply just the Bernoulli equation between those 2 points. And you neglect, because it's very short, you neglect friction, and you neglect also the elevation change. By doing that, using mass equation, then making some substitutions, you end up with this equation for ideal liquid. And the big trick for all choke models, we stick a constant called CD, okay, that accounts for vena contracta. It means, well, the area that the fluid is going through is not the full throat area, because you have this vena contracta effect that the fluid doesn't recover, but very slowly it starts to expand and stick to the walls. Okay, here is just like a jet. So by changing that CD, I'm able to match the values that I measure. So the manufacturer comes, they test their choke in a bench, and then they measure with that equation, and then they find the coefficient where the equation gets equal to the measurements. Okay. Another assumption is that we normally in a choke, we don't measure pressure here at the throat. We measure pressure here, downstream. But I told you that normally in a choke, we say that the recovery of pressure after the throat is very, very small. Because you lose pressure, and the idea of the choke is you don't recover this pressure. Okay, so you can say pressure at the outlet is very similar to pressure at the throat. But there are some models that they try to say, well, it's not. Okay, you have some expansion, and they try to quantify, to include that expansion in the equation. But sometimes doesn't give the best result. So that's what we left last time. For real oil, we have to include this BO. Let's now make a short comment to start our lecture. So today we're going to have, so you will see how the choke equation for gas looks like. And it's going to look similar for multiphase. Okay, we are not going to cover it here, but it's going to look similar. And we're going to do an exercise. And later today, we are going to go to single phase flow, which is useful for when you have only oil or when you have oil and water mixtures. And that I'm going to make a small comment on that. And we're going to have an exercise on this. And then if we have time, I'm going to introduce a bit about ESP, which stands for electric submersible pump. Okay. Okay. So let's see, you have a choke, okay, and this choke I'm going to make it adjustable, okay, because I want to see something. Okay, I have an adjustable choke of any type, cage or any type, and the equation was Q there was a 2 here. Equation. When you have an adjustable choke, this area is changing, right? Is changing. When you have a bean choke, that area is just constant. Okay? When you have adjustable, it's changing, or I can modify depending and it's usually the position of this guy. Okay? The position of the how do we call this? The stem, the valve stem. Okay? On the position of the valve stem. Okay? Which we are going to call L. So area 2 is a function of L, okay, depending how high this guy is, right? If it's very well separated, that area will be very big, and if it's lower, that area will be very small. Yes? So let's make here, so let's say when L equal, let's say L max, okay, that means fully open. A2 is max. And when L equal to L min, that means fully closed. That means A2 is 0, basically. Now let's make an experiment, because there is something interesting how choke behave. And I'm going to put here L from L minimum to L maximum. And here I'm going to put the rate, okay? Let's use the rate divided by the rate maximum, okay, when the maximum is 1. And I'm going to say this plot is made by QP is fixed, okay, the same delta P. Somehow I maintain the pressure at the inlet and at the outlet of the choke constant. And I'm trying to see what is the rate that will flow through the choke when I'm changing the opening. Okay, I have the same delta P. I open the valve and then I measure the rate. I close the valve. I also measure the rate. That's what I want to plot here. Okay, so let's see. When it's at the minimum, what is the rate? When the opening is very small or 0. I just don't have rate, right? This will be 0. And when I open it to the maximum, okay, it's maximum, it will be 1. That's fine. So these are the endpoint and the 2 endpoints. Okay. So depending on how the choke is built, depending on what kind of choke, you might have different behavior. Okay. Sometimes you have a linear relationship. That means if I move up 1%, this guy Okay, I'm going to get 1% increase in rate, 2%, 2%, 3%, 3%. So this is a linear opening choke. Okay, which is very good. But sometimes I have other chokes which are like that. Okay, and these chokes, it means that I'm changing L, you see, and I have almost no change in the rate. I open, 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 no change in the rate until I reach some L when it starts to increase dramatically. Okay, so these chokes are very good at controlling at low rates, right? I can have a very precise. Let's say I'm working. Let's say Q max. Okay, let's say Q max is 1,000 barrels. Okay. Hmm. Okay. So for the range of the lower rate, let's say around 100 barrels, okay, per day, you're going to have a very fine control. Okay, you want to put the well in 101, 102, you're going to be able to do that because that choke gives you a very fine control for the low rate range. Okay? But once you enter into the higher range, let's say 500, 800, 1,000, okay, if you make a small change in the choke, it's going to change dramatically the rate. Okay, so this choke is good for low rates, but it's not good for high rates because I have very poor control for high rates. And I have another type of choke, which is actually the opposite. It's like that. So let's put it in a different color. Okay, so the black choke is good control for low rates, and the blue choke is good control for high rates, but poor control for low rates. Because if you are increasing, you change here a little bit, a few millimeters, the opening, it changed dramatically the rate. So it will jump. You have 100, you change it, jump it, you have 500. And let's say you want 300. So you have to change up and down. You cannot regulate. Okay, it's very difficult. But once you come to that region, okay, let's say you are 80, 90%, you open, then there you can get 1,920. You can get exactly the number you want. Okay, and that depends on the way the chokes are constructed. To avoid for erosion, maybe it's better cage, but cage maybe behaves like that. Okay? Maybe this is better for other things, but maybe behaves like that. So you have to be careful when you select the choke where, what range are you interested and how sensitive the opening is to on that range. So here we say good control for low rates, poor control for high rates. Okay, and ideally we would like to have a choke which is something like that, where we have a good control. See if I don't screw it up. Good control, and okay, or I need to exaggerate a bit more. Okay, actually not like that, but let's see. Okay, where I have still relatively good control for low rates and I have relatively good control for high rates. And medium rates, well, I sacrifice a bit, but I have good control on both the upper and the lower range. Okay, that's just a comment about the operation of the choke. And now let's go for the gas, okay, which gas was the challenging and what the exercise we're going to do here. So the choke equation for gas, okay, and we depart from the same equation, dP plus density U du, okay, equals 0. And then this guy is a function of pressure, so we have to put it together with pressure. So we get here U1 squared minus U2 squared. And remember, 1 is choke inlet, and 2 is okay. Here we have 0.5. That's going to be the same. And now I have dP over density. And I have to integrate from P1 to P2. Now, one of the things we make with gas, one of the assumptions, okay, is that U1, U2 is much, much bigger than U1. Okay, for liquid you have, because the density doesn't change. So in that case, they are more or less comparable, okay? But for gas, due to the change in pressure, U2 is always much, much bigger than U1. So you can change that expression now will be 0.5 minus 0.5 U2 squared. Okay, so you end up just with that expression. And if you remember, the density was P divided by Z RT. Okay. And we substitute in our equation, we have integral okay. Now, there is a problem with gas that we already saw on the exercise we have done yesterday, or that you have done yesterday. Okay? That the temperature is changing also, and the temperature changes quite a lot. Okay, the temperature change in our example from 90 to 65 is 25 degrees change, and that's going to affect the density. So we cannot, just like in the IPR case, we were very happy with temperature because we took it out from the integral. If you remember here, okay, we have that integral, but we say temperature is constant. We can take it out of the integral. Here is not so simple because temperature is also going to change. Okay? So the way I try to model this process, okay, so I try to model the process, the expansion process in the choke is modeled, or the thermodynamic, okay, process as adiabatic. Okay, and you told me, well, you were assuming that it's isoenthalpy, right? In this exercise we did yesterday. So why don't you have the same assumption? Remember here, this is between outlet and outlet of the choke. When you have already, the velocity has increased again. Okay, where is it? It's between exit and exit. If I want to make it between these 2 points, then the kinetic energy cannot be neglected. You have to include it. The enthalpies between these 2 points are not the same because you have the kinetic energy. Okay, in that equation, we are saying by using this, basically, we're saying all other energies don't change much. Okay, remember that this accounts for the energy that is coming in. That should be potential energy, should be kinetic energy, and should be internal energy of the fluid. Okay? Here we were saying, well, it's only enthalpy. We are neglecting kinetic, we are neglecting potential, we are neglecting everything else. So, but another assumption I can make is that it's adiabatic, in which I don't have any pressure, any temperature loss with any heat transfer. So this is no heat transfer with the environment. So if we do that, we end up with saying that P1 over density K should be constant from P1 to P2. Okay? And that's a demonstration. If you go to any thermodynamic book, you say for a real gas, if I have an adiabatic process from P1 to P2, that's the relationship that has to be honored. P, okay. So that means that density, right? Density, which is what I had here in this equation, density, it's P over 1 over K divided by C 1 over K. Yes, C is this constant. Yep. Okay, and instead of using this equation that I substitute T, okay, because I don't know how T will change, how Z will change, nothing, I just use this equation for adiabatic expansion. So instead of using this, okay, I use this one. So I say the integral from P1 to P2 dP, and then I have to substitute C 1 over K, P 1 over K dP. Okay. And then I integrate. And what do I get when I integrate? That I have to use my for those of you who are good in math, you can check. Okay, then I take as a common factor P1, so I say P2 divided by P1, K minus 1 over K minus 1, that will be P1, K minus 1 over K times C 1 over K okay. Okay, now we have to introduce this C, okay, and we have to say, so we are going to make some changes here. So the first is, I'm going to call P2 over P1, I'm going to call this Y, and this will be the pressure ratio, okay. C, we know from the equation above, right, that is P over density of 1 over K. So, and that is going to become constant from 1 to 2. But I usually know the properties, or I can calculate the properties at the inlet of the choke. Okay, so if I apply this equation at position 1, okay, I'm going to get P1, C will be equal to P1, density 1, 1 over K. Okay, and here the density 1 can be expressed as P1 over R H1 P1. Okay, and then I substitute on that equation. So C is P1 K minus 1 I think so. Let's see if I didn't. Yeah, I think that's okay. Yeah, I think that is yeah, I think that is correct. Let's see. Let's go back to this expression I had. So P1 yeah. Okay, so let's substitute. I have y k minus 1 over k minus 1. This is this guy here. Now I have P1 k minus 1 over k. And then I have C 1 over k, which is, I think this expression is not correct. I think I have something wrong here. Is this expression correct? Density. So when I substitute here, so I substitute this guy here, I end up with 1 over k. Okay, so it will be P1 is wrong, right? Times P1 minus 1 over k, right? And how much is that? It's fine. Yes? Are you sure? Oh, we have to divide by 1 over k. K is not only c, but we have to say c 1 over k. That gives you P1 k minus 1 over k. Yeah, somehow last year I just I know why I skipped this complexity. So yeah, let's use that. I think what I used in class last time was without replacing the equation of state. So let's see if we get something better like that. Okay, and then C over 1 over K will be P1 1 over K divided by rho 1 just at 1, right? No, because I have rho 1 minus 1 over... Should it be 1 over K squared or... Huh? Yes? Yeah, then I'm making a mistake someplace. 1 over K. Okay. Okay, so let's put the rest that we know. K minus 1 equal to minus U2 squared. And here we have to know how do we handle this C. So this C I'm evaluating at 1. So I know that C is like that. But I need C 1 over K. Right? Because that came from the integral. So it's not, I think here I made a mistake last time. Here it should be 1 over K, right? Because when you, 1 over K squared. I think so. Okay, so let's substitute that here. P1, 1 over K divided by density 1, 1 over K squared. Okay, and I end up with U will be, just like in the other case, U2 will be the square root of U, which is negative, so 1 minus y, k minus 1 over k, k over k minus 1, p1 k minus 1 over k, density 1, 1 over k squared. Okay, and in this expression I substitute, so I substitute here, and I'm not going to do it because that will be more homework, but P1, then here I substitute density 1 will be P1 over R set 1 T1. And lastly, what is the definition of U2? Last time, when we were doing the liquid choke, we put it in terms of the rate, okay, the local condition rate. So, what is the local condition rate? QG, right? Well, actually is we can say it's the mass flow divided by the density of 2 and the area of 2. Yes? And this CD, okay? We're going to put the CD later. But density of 2, we can use that expression, pressure over 2, density of 2, 1 over K will be equal to pressure 1 over density of 1, 1 over K. Right? I think that was the expression of the, because C is constant. And then we can say that density 2 will be P1 1 over K divided by P2 times density 1. And then again we can substitute this expression here. Okay? And we end up with mass flow is equal to so density 2, area 2, and then we have the square root of this guy here. Okay, but remember, we don't want mass flow, we just want standard condition rate. Okay, so we know the mass flow is equal to the standard conditions rate times the density at standard conditions. Okay, and the density at standard conditions is P standard conditions, T standard conditions, okay, R, QG. And then I say at the end QG will be equal to density to area to P standard conditions R over P standard conditions times that square root P1 Okay, now I substitute or I use these definitions for the densities. Okay, for the density of 1, this density of 2, I use that definition, and I end up with, we are almost finished, that we have here, I think, okay, with that expression. Okay, we end up with that expression. When we simplify, I'm not going to simplify, maybe I made a mistake someplace here, but I don't think so. So if you simplify, you end up with that expression. Okay, which is, first thing to notice is that we don't have the delta P. Okay, we have the pressure ratio in this equation. Okay, if you remember, for the liquid, we had the square root of delta P. Now we have the pressure ratio just because of the expansion. We have all of these properties, and I want to express them in terms of something that I know, one condition that I know, which is the inlet. Okay, so everything is expressed in terms of 1. Okay, and at the end I have the area of the throat, and I'm modifying with this CD, which accounts for the vena contracta. Okay, so that's the equation of the choke, and that's the equation we are going to use. This equation is valid for the subcritical regime. Okay, that means, if you remember our curve, delta P versus Q, okay, that equation is valid for this regime. Okay, so then what do we use for this regime here? That's just a straight line, right? So for that, I just have to calculate for this regime simply QG will be this function at the critical Y. Okay, at the critical pressure ratio.
And how do you know what to do?
We gave the expression before, right? Or last class. Here, okay, that expression. Okay, so you know it's just a constant, so you can evaluate at this point, and you know the rate will be the same for all other points. Okay, so in that expression, you come and substitute on that expression the critical Y. Okay, and then you find the rate, and it will be the same rate for all of them. Okay, now to wake all of us up, okay, let's make an exercise. And the exercise, it's on, let's see, I think it's on the class exercises. You can find it on the website also. It's called Choke Performance Dry Gas.
My question is, what if we establish wrongly the critical parameters?
Well, it can happen, especially when you have multi-phase flow. But,
The impact.
well, the impact is you will be wrongly characterizing this part, okay, the critical rate. But that's something you can measure on the field. You can change slightly the pressure downstream, and then you can see if the rate changed. If the rate doesn't change, then you see that you're in the critical regime. Okay, so let's open that exercise of the choke. Okay, it's called choke performance. And here I have to make a comment that you go to the equations, is exactly the same equation we have been using. Okay, the only thing is that you have now some coefficients, okay, and these have to do with units, changing units. You want this rate to give you in standard cubic meter per day, so you have to include this 24,3600 someplace, okay, and also pi and other constants are in here. So this Cn is a unit coefficient, okay, and also includes the CD. And the CD in that case, if you go to the first page, is 0.865. Okay, they define for that type of choke the coefficient is 0.865. Okay, so let's see what else we have. We need standard conditions, pressure and temperature. We have that Cn. We have this adiabatic constant, which is the Cp over Cv. We have the specific gravity of the gas, the inlet temperature, the critical ratio. Let's see the equation, Alt F11 to see the equation. And you see it's exactly the equation that I wrote, okay? 2 over k plus 1, k minus 1. So last class I told you was a number around 0.5, 0.6, okay, and in this case it's 0.546, which is as we expected. And you have the diameter, that the diameter of the choke is going to be used when calculating this A2. Okay, so I propose we keep exactly what we have done in class. We have P at the inlet is constant, and then we are changing the P at the outlet. Okay, and we should get exactly this curve, and at some point we should get a critical flow. The equation we are going to be using is called this one, orifice rate metric. Okay, and inside you see I have an if. Okay, if I'm above the critical flow, simply use the critical flow ratio, calculate that rate and report it, no problem. If not, I use the full equation, which is the equation that I wrote before. Okay, Cn, etc. Okay, so let's use that equation, but that equation takes the input in kilopascals. Okay, so I have to change first from bar to kilopascal. So that will be this guy times 100, right? To go to kilopascal. And then I drag it here, and also I drag it down. Now the delta P is just the difference between the highest pressure minus, oh, this is in bar, okay, so it's minus this one, A14 minus B14. That's just to make the plot, Okay, we are plotting delta P versus rate. Okay. Then I calculate the pressure ratio, and that will be this pressure pressure ratio is P2 divided by P1. Okay. So I ask you now, from where I'm going to have critical flow? Am I going to have it from here to here or from here to here? You see, the critical is 546. Okay, so it's very close to that number. That's where I'm going to get critical flow. So the critical regime, will it be from here to here or from here to here? You can look at the pressure drop, right? If you look at the drawing we did, right? That's the critical delta P. Okay, and then if I increase it, that's going to be the critical regime. Okay, when the pressure at the discharge is lower. Okay, so the critical regime will be from here up. Here, all the rates should be constant, and here, for all of them, the rates should change with this non-linear expression. Yes? P1, this one? It's just simply the difference between P1 minus P2. P1 minus P2 in bar. Okay, I want to calculate in bar. Yeah, I'm just changing units from bar to kilopascal.
This is values. How do we obtain?
That is for the well. It's not exactly equal, okay, but it's for the well that we were working before. In class 2, I think, was it? Let's see, I think it was here. Okay, it's for a similar well that we were using before. That here you have the choke is, I think the rate we are trying to find is here, okay, 200. And then we want to bring it to 40. Okay, so we want to see what will be the rate. I'm planning to put on that well. Where is it? I want to put on that well an orifice of 22 millimeters. Okay, so I want to see if that will give me the pressure drop that I want. Okay, I want here exactly. We're using 204, so we should be someplace here. We are using 40, so we are going to get a rate of around 1.3. Okay, so let's make just maybe good to make a small example. So P1 will be 204 bar. P2 will be minimum, will be 40 bar. And the rate that I want, desired, okay, is according to this plot is like 1.25, okay, 1. Okay. And the choke that we use, the choke that we propose, someone proposed off the shelf, is a diameter of 22 millimeters. Okay, choke 22.3 millimeters. Now, we are not going to calculate just one point. We want to calculate the whole plot. Okay, but in reality, the choke will be operating only at one point. Okay, at one point here. So I ask you, is the choke going to be operating in the critical or subcritical conditions for this well? Okay, this well I think is called EVA, and this well was given in day 2, and we can maybe copy the equilibrium here such that we all of us know what we are talking about. I'm going to put it here. Okay, so this EVA, if I say I want a rate of 125, okay, the pressure required, and here I'm making wellhead, okay, that's wellhead equilibrium. Okay, where I have the intersection here, that's P required, and that's P available, and that is 204, and this is 40 bar. Okay. And I want to define a choke for that. I'm trying to find a choke for that. So I ask you first the first question. In which regime are we? That's very simple, right? We just say Y will be P2 over P1, and this will be 40 divided by 204. And how much is that? 204? 204, I think. Oh, how much do we have in the Excel sheet? Yeah, 205. Okay. How much do we have here? 195, and that means the critical is something always close to 0.5. So if my Y is less than the Y critical, this means I'm in the critical regime. Okay, and we're going to see that soon. So and that's the rate I desire. So let's see if this choke of 0.22 will give me that rate. Okay, so I made a plot. Okay, that's the point really that I want, this point. That's the one that I'm interested. But I'm making the whole curve just to show you that it actually looks like what we discussed in class. Set I, that's the deviation factor at the inlet, so that we can calculate. If you remember, we have this equation called C factor standing. So we go to that equation, C factor standing. P1, it should be in bar. Can I use this one? T1, that temperature of 1 is here, someplace here. And I have to, yeah, that's in Celsius, that's fine. Specific, that I have to block, okay? Be careful. The specific gravity of the gas is here, and I also have to block it. And the unit will be 2. And I hope I didn't make any mistake. P1, T1. Okay? And actually it's constant because the pressures are always constant at the inlet. Okay, now comes the difficult part, which is the rate. And the rate, we have to use the equation called orifice rate metric, where we need P1, P2, gamma, Z1, T1, and K. And this should be in Kelvin, and these pressures are in kilopascals. Okay, that's the way the equation was derived. and D is in millimeters. Okay, so let's use that equation. Orifice. Cn, remember it's a coefficient that has inside the CD and the units changed. So we block it, will be the same for all points. Choke diameter, that gives you the area tool in the equation, and that we have to use in millimeters. Block it. P1, that's the one that is in kilopascals. P1 is here, I don't block it. P2 is here, I don't block it. Gamma, it's here, and that I block. CNT, P1, P2. C1 is this guy here. C1. T1, it's in Kelvin, be careful, is this guy here. And that I should block. And K is not permeability, but ratio between Cp and Cv, and it's this guy here. And then I block it and click enter. Okay, and I got 1.5 e to the 6. Not sure if did you get same number?
Yeah.
Yep. Yes. I C. The C factor, it's this Cn. Or you're asking about this one? Yeah, C factor standing. So pressure in bar, this pressure. Huh? Okay, the same number. Let me drag it down to see. Now if you can just plot, I think the choke performance, it should be plotted on the, yeah. Yes. Okay. Just the ratio. Yes.
Não, não, não. Não, uma série. Depois? Não, eu quero dizer que
Okay, the choke curve looks like that, exactly like I draw before. Okay, and I'm going to ask you if it does this choke works or not for what I want. Okay, does it work or not for that's a choke of that's a curve for P1 205 bar for an orifice of 22.3 millimeters. And what else? Nothing else, right? I think. Okay, so I ask you, does it work to get the rate that I want from this well or not? Does it work to get the rate that I want from the well? Remember the well that we are dealing with? Let me close that. No, cancel. Let me just copy that here. Okay, remember for what I want is P1 205, P2 is 40, so that gives me a delta P of 165 bar, right? And the Q that I want desired is 1.25 e to the 6, yes, per day. 25 or 35? 25. Okay, that's what I wrote here. So if we go and use these two, 165, right? We use 165. Yes? No, that's what I want from if I go on the equilibrium of my previous well, okay, I said I want to produce, if I leave no choke, right, I will be produced at 2.80 something. But for sand purpose, my reservoir engineer told me if I produce this rate, I will damage the formation. Okay, I will start producing too much sand. I will affect the stability of the wellbore. So he said, take it not maximum than 1.25. Okay, so here I'm calculating that I need a choke to breach 160 bar and a rate of 125. So that will be 125 is here. Okay, so the point I want is here, and the point that I have with the choke is here. Yes? So the choke doesn't work for that purpose. So what do I have to do for my choke curve to pass exactly through that point?
That discussion that we had yesterday, we can increase pressure.
Okay, I want a choke curve that goes exactly like this and goes up and gives me exactly that combination, right, of delta P and Q. So if you remember, maybe not, what we discussed yesterday, we say that the curve of the choke is changing with two things, right? Pressure or the diameter. Is the inlet pressure going to change?
What?
The inlet pressure of my choke. No, right? That comes given by this equilibrium. Okay, so the inlet curve is always the same. That is not going to change. 205, that cannot change. But if you see, the other option we have was to change the diameter. If I change the diameter, I will get another curve. Okay, so do I have to increase or decrease the diameter? Decrease, right? Why? Because I want to get a higher pressure drop. A smaller rate, yes. So let's try with, I'm not sure if we can use the solver, okay? The problem with using the solver is that this is a very ugly equation. If you see the equation, how it looks like, it's very ugly. A lot of square roots, a lot of differences. So solver, I'm not sure if it will manage to solve this problem, okay? But we can try. Let's try. So we say QG desired, okay? Let's try. If it doesn't work, we do it by hand, okay? So Q desired was due to the reservoir engineer. He told me I want exactly 1.25 e to the 6, okay? And then I define here an error between these two numbers. Okay, I want to have an error. That's what I'm going to drive to 0. And let's say that this error will be open parenthesis the number that I calculate minus the number that I desire squared divided by the number that I sorry, just something like that, divided by, and then I squared. Okay, so I'm making the difference, right? Because I want to minimize that difference. I'm dividing by the desired is something called normalization in math. Okay, I do it such that the number won't be very big, just that the number will be between, when I normalize, let me just make a short comment. Okay, so I'm saying here Q desired, okay, 1.25 e to the 6, and then I have the error, which will be Q calculated minus the Q desired, and when I divide by Q desired, okay, this gives me Q calculated divided by Q desired minus 1. Okay, so when I take that difference, this is a number, let's say bigger than 1, okay, between 0.5 and 1.5, for example. So this will always be a small number, and the solver likes to have this small number. If I don't do that, if I don't normalize Q calculated minus Q desired, this number might be very big. Okay, it might be extremely big, because I'm talking here on millions. So solver doesn't like these really big numbers. And the next step I made, I just make square, just to make sure that because solver takes it to the smallest, right, to the minimum. So I want that this will be always positive, thus the minimum is when it's 0, when the two of them are the same. Okay, so let's that error, let's see. Okay, so it's very small, and let's see now if the solver works. Let's see if we are going to, it's going to cry or not. Solver, please take this error that I have, take it to a minimum by changing the value of the diameter. And it found a solution, 20.90, okay, millimeters. So that's the choke size I have to put to 20.9. If I use now a diameter of 20.9 millimeters, okay, I'm going to get exactly through that point. And the way I go, I say, well, how much in inch, how much is that size? And then I find a choke which is, you know, remember, chokes go in 1/8 of an inch to 2 inch, and they go in increments of 1/64. So I find the number that gets closer to 20.9 millimeters. How much is that in inch? It's like almost an inch. Okay. Okay, 20.9 over 25. That's almost like an inch. Okay, 0.82 of an inch.
Why 25?
Because 1 inch is 25.4 millimeters. Okay, so it's just dividing to know how many inches we have, and then from there you can select your choke. It's probably going to be 3/4 plus 1/64 or something like that. Okay.
We go back to the
Okay, so I said that's what I want. This is what I have. So I want to make the two of them the same. and I create an error. And first I want it to be always positive, so I'm not sure if it will be, I don't want it to be plus or minus, I want it to be exactly 0. And then I normalize. And this trick of normalize, I just do it because the solver to get a smaller number. Okay? When I'm talking here, subtracting millions, I'm going to get huge numbers, 500,000, and solver doesn't like sometimes big numbers. Okay? Now, should we do one more thing before we leave this exercise and take a break? Yeah?
Could you repeat the solver step?
The solver, I wrote here the desired, okay? Then I create the error, which is what I calculate minus the desired, then divided by the desired to normalize, to make the number small, and then I square, okay? Such that the difference, no matter if it's negative or if it's positive, when I square it, it will always be positive. Okay? And then I come to my solver and say, solver, please send that number to 0. Okay? By changing, you have to change what? Inlet pressure you cannot change. Downstream pressure you cannot change. The only thing you can change is the orifice size. Okay? And then you click solve, and then it should find a solution. He managed to deal with that complicated equation. Okay? With this, which is a very complex equation. Okay, it's a very ugly equation. You have a lot of exponentials, you have square root, you have everything you don't want, you have it there. So that's an example of choke design. Okay, choke design. Okay, so that's.
You calculate after that, you will come give the image.
Well, it's automatic because when I change here, it just updates automatically the table. Okay, because here it depends on that diameter, so these values will change, and this you will have a new curve now. Now, you have this question, right? What happens if we change the inlet pressure? If I told you if we increase the inlet pressure, how will the curve change? We can do it here, and you can see it very quickly. So let's make one more thing, and let's change the inlet pressure to 250 bar. Okay, and see now the new values we have. So let's get first 2.5. Okay, so the last step here is to, what is the effect of inlet pressure? Okay, what is the effect? That's the original. That's for P1 equal 205. Okay, now let's say with P1 250 bar to see where it's going to fall. And what was the critical, if you remember? Why critical? It's 0.546, and that is, yeah? Okay. Yes, but yeah, you can try one thing to not normalize. Let's try just one thing. If we go to 22.3, let's say if it works. I want to drive, so you open the solver. So you say, I want to drive this number to a value of, instead of creating the error, instead of creating the desired, you just say value of, I want to drive this number to a value of, and here you say 1.250123, 1.1,250,000, okay? By changing the diameter. And let's see if it works. I'm not sure. Okay, here I should drive this one. Okay, it also worked. So I don't have to use this, forget about normalization and everything. So just, in this case it works, just use the solver to change this number that you now should have 1.5. You want to drive it to, be careful with the number of zeros, 1,250,000, and by changing this. Okay? So, one more thing before we take a break. I think we all need a break. But, so one thing was, we were asking the effect of inlet pressure. Okay, if you increase the pressure, will the curve will be like that, okay, on the outside, or will it be on the inside? So let's try, I'm going to try it. You can try to do it if you want. But we said now the pressure will be 250 bar, the inlet pressure. So where should we have the critical delta P? The critical delta P is P1 minus P2, right? And that will be, we know from here that P2 over P1, 546, that's the number we are getting, right? The critical, 546, okay? And then I say, then P2, P1 minus 0.546 P1, that will be, you told me yesterday, 4, 3, 4, right? P1, that will be the delta P critical. And how much is that for 250? This is 250.
It's 108.5.
Okay, 108. So here, if you see the critical is someplace here, okay, for 25. How much is it for 25?
No, is there 108?
No, yeah, but for this one, for 205. Here we have the curve for 205. Okay, so how much is it for 205? Eight point 97 bar. Okay, so that's exactly close to 90 here. And then for P 250, it should be 108, which should be close to here. So we know the critical point is there, but we don't know if it will be to the right or to the left. Okay, so let's do that. Let's change P, is very simple. We change, instead of 25, 250. Okay? Don't change the orifice. Okay, the orifice is 20.9. Okay, that's the orifice it works. So, where is it? Is it to the right or to the left? Look at the critical rate. Okay, the critical rate is 1.5.
It's to the right.
Okay, if we go back to our plot, okay, 1.5 is here. 2, 4, that's 1.6, so 1.5 will be here. So the curve will be like that, and it will be on the outside like that. Okay? So I was correct, okay, yesterday, no? To the right. Let's see the evidence. We have the evidence, so that I show my wife also. Okay, if the pressure is bigger than P1, I'm going to be to the right. Okay? Yeah, so I did this long confusion, but you can explain almost everything. When you have the equation, you test it, and you show, well, actually it's to the right. Okay? Okay, I don't have to argue anymore.
And the note saying that that's not correct.
Okay.
That's why pods are going.
Okay. And you can compute if you want. This is not an exercise to deliver, but you can change to place, you see, the effect of P, the effect of the diameter, but very helpful to allow you to see if your choke, first, so for choke, very important two things, okay? First, in which regime I am, if I'm here or here, and that's something I can verify very quickly, okay, by making the ratio, okay, by making this ratio. And the second thing, find the diameter, okay? So now let's take a break. Let's say 15 minutes, yeah? Okay. Okay. let's um, let's talk about flow of liquids, okay? And flow of liquids, it has limited applications, okay? Sometimes it can be used for dead oils, okay? Like this field that we were working in Colombia, Rubiales, it had a very low bubble point pressure. Low bubble point pressure, okay? That means that the gas started to come out of solution at a very low pressure. So you could use really this equation for liquid for almost the whole system. You can use it for when you have a mixture of dead oil and water, okay? Because many fields don't produce just water, they produce just oil. They come out with a lot of water. And you can use it for oil transport, flow lines, and pipelines. Okay? So it's not something that we don't. There are some cases where we can use it, and it's very useful. So that's why we want to, just to introduce it. And I guess most of you remember it's quite, trivial, but we are going to make a refresher. So you remember we have one position 1 in a pipe and a position 2 in a pipe. Okay, this is a pipe. And the Bernoulli equation, what does it say? The P1 divided by the density plus Ci, C1, plus the velocity 1 squared over 2g, right? The energy in point 1 minus the energy that it loses, okay, which I can call HF, okay? So these are energy losses, will be equal to the energy in 2, which is P2 over density Z2, okay? So it's the same equation we are going to use here. However, there are a few things, a few differences. HF, if you remember, we had two types of losses. One of them was localized due to restriction, due to change of direction. So we have two parts. One of them was, well, actually not F. Let's call it just HL, H losses. Okay. We have H accessories due to flow restrictions, change of direction, or we have F due to friction with the pipe. But at the end, if you see, if we had, for example, the subsurface safety valve, right? If we have in our tubing, we have our surface safety valve, which it could cause a restriction. Okay, so in that case, we say we can model restrictions. HA has an equivalent length. Thus, almost always we use this HF. And what is the expression for HF? Due to friction in pipe, friction factor times the length of the pipe divided by the diameter, B squared over 2G, right? Where F is the friction factor. So remember what we want, okay, in all for gas, all of our developments, we are trying to get an equation in which P1 is a function of, is not friction factor, okay, it's a function, let's use another F, a function of P2 and Q, right? Or we want a expression P2 is a function of P1 and Q, or we want an expression where Q is a function of P1 and P2. And we can get it with this expression if we just rearrange terms a little bit. Okay, so the first thing we make usually for liquids, okay, B1 is very similar to B2. You have no big changes because the density and the volume really doesn't change that much. So a common assumption or a typical assumption is just that, yeah, these two are the same. Therefore, I take them away from the equation. Okay, so I end up with P1 over density, gravity, Z1 minus FL V squared over V to G equal to P2 over plus Z2, right? And let's say we want to calculate the pressure available at the discharge of the pipe, okay, which is P2. So let's clear P2, okay? And P2 will be then, P2 will be equal to P1 plus Z1 minus Z2 times the density times the gravity minus FL over phi V squared 2G, and density is someplace here. Yes, I think so. Yes, okay. So you see, we almost have that expression. P2 has a function of P1 and rate, okay? Z1 minus Z2, that is, if we are talking about a tubing, okay? That is typically the difference in height, okay? If we are talking about a tubing, we know that 1 is at the bottom hole, 2 is up here. So usually, Z1 minus Z2, that gives you a negative number, okay? That gives you minus H is equal to Z2 minus Z1. Sorry, Z1 minus Z2. That's what you have in the equation. Okay, H is the height of the tubing. So we end up with P2 plus minus H, okay, minus, and then the next challenge is to have the rate. Okay, we want to have the rate. And for the rate, we can say that Q oil divided by the area, right, the cross-section area of the pipe, cross-section area, that will be my velocity. So I substitute, so velocity squared will be QO divided by pi phi to the 4, and here we have someplace 16 p squared, that's correct. So we have F L over, and here L and H could be different, okay? H is the difference in elevation, and L is the length of the pipe. So if you have a tubing which is inclined, the H will be just this, but L will be the whole length. Density 2, and here we have V squared, which is QO squared 16 divided by pi squared phi to the 4. And there you have your equation that relates P2 with P1. So if you see, the pressure at the discharge of the pipe will be equal to the pressure at the inlet of the pipe minus, and here is very clear to see the contribution, minus the gravity hydrostatic column, right, minus the friction. Okay. Of course, here we're making some assumption. Okay, we normally work with QO, right, at standard conditions. And if you know, QO is just BO times QO. Okay, but in all of this development, we are assuming that BO is very similar to 1 for this development. If not, you have to make it in sections, okay? If not, you have to split the tubing in sections, calculate the rate, the BO, for each section, and then you have to calculate the local rate, and then you have to use that equation in segments, like what we have done for gas, okay? But to make it simple, to make our life simple, we are going to assume BO equal 1. And you know, F is in this case is the Darcy Weisbach. Okay, Bernoulli friction factor that you obtain by you cannot use the same trick that you use for the gas, but you have to use that chart that we discussed a bit before. Okay, where you have the Reynolds number, you have to calculate. That's velocity, diameter, density divided by viscosity. And we have here the relative roughness, which is, you know, if you look at the wall very close, is that the distance of, okay, the valleys is that distance. That will be E divided by the diameter. So you find out your Reynolds, you find out your roughness, and then you see depending on where you are. If you are here, it's the same case as for gas, but sometimes for liquid we are also in this region. Okay, so that's why we have to use this chart. Okay, there are many, so be careful. Remember, there is also F fanning. Okay, and the F fanning is defined, the F Moody is defined as 4 times the F of fanning. So be careful which friction factor you're using. And usually, if you're working in field units, they like to use very much fanning. Or for multi-phase flow, they like to use fanning. So be careful which friction factor you are, because they are very different and you have a factor of 4. If you use the wrong friction factor, it's basically you're either dividing by 4 or multiplying by 4 your losses, okay, your friction losses. There are many expressions for the friction factor, If you go search, I think I took this from Wikipedia, so I'm not going to get sued by anyone, I hope, by pasting it here. But if you go to that website, you will find tons and tons and tons of expressions for the friction factor. Okay, you have the Moody expression, Wood, Eck, Churchill, Jane, Churchill again, Holland, etc. You're going to get a very long table. I think I here just copy part of it. Yeah, here there are more. So I just want to fill the space on your notes. Okay, many, numerous. And every time they fix something, a small detail, okay, you see the equation sometimes becomes very long, very ugly, and they say, well, Brad reproduced the data much better, all kind of changes, all kind of things, okay? So note that some f expressions are implicit, okay? Like the most famous is Colebrook, okay, and that's an implicit expression. Let's see if I have it someplace here. It's not here. I think it's similar to this one, but it's not exactly the same. Okay, let's take this one. Or yeah. Well, we have here no. So some of them are implicit. Okay, that means that I have f on both sides. Okay, I have f here and I have f here, and then I have to use root finding a numerical solver. Okay, to find the value. I have to assume an f, verify the f. Is not, I have to repeat once more. I have to use numerical solver. And I have also explicit expressions. Okay, and these are the ones that we are going to use, and most of the table are explicit expressions. And we are going to use, because, not because I'm biased, but because, well, maybe I'm a bit biased, we're going to use one from a Norwegian professor from my university, okay? Not for any reason, okay, but that's the one that we are going to use in this course, but you can use whatever you want. You go to the table, you like this guy, maybe he's from Mozambique, so you go and you use that expression, whatever you prefer, okay? In this course, we're going to use this expression that is a professor called Holland, that I think he retired. He was working at the university I come from, and this was in the 1980s. He came with that expression. And so it tells you f minus 1 over 2 is 1.8 log of the relative. We are using phi, right, for diameter, 3.7. Relatively easy to use and is also very accurate. Okay, so that's the expression we are going to use. And here you have also to be careful. So that, remember that we have in this plot we have two regimes. Okay, this regime we call it the turbulent. So for that we use all of those ugly equations. And if it's laminar, laminar means Reynolds more or less below. Yeah. So say you have 2f, f for laminar. okay, where the fluid goes in sheets. So that's when the Reynolds is typically below 2500, or if it's turbulent, the Reynolds is bigger than 2500. Okay. In pipe, in real life, you go to the lab, those limits might be, people show that actually the transition happens at different Reynolds. There is a big discussion here, there. For practical purposes in the field, we assume 2500, that's the transition. Okay, and we have this equation. Where was it? Here. And that's the equation we're going to use for our problems with when we have liquid. Okay, that's the equation, and you can use any way you want. If you have P2, okay, you have P2 and rate, you can calculate P1, or if you have P1 and rate, you can calculate P2. You can calculate the available pressure at the discharge of the pipe or the required pressure at the inlet of the pipe. So I think we are ready to make an exercise. Okay, that exercise, I think it's a class exercise also. I have to give you some more home exercise. Otherwise, it will be very boring. Okay, so we have this system. It has only oil. Okay, you can open, it's in class exercise called undersaturated oil equilibrium. And in this exercise, for some reason, there is a dead oil, so the exercise here is class exercise. Undersaturated oil equilibrium. Okay, and here the bubble point pressure is very low. Okay, so it's almost like a dead oil. And this happened in very heavy, usually it's a very heavy oil reservoirs that you probably don't have here in Mozambique. So we are going to make bottom hole equilibrium. Okay, that's the intention. We are going to make bottom hole equilibrium. We have a well. Okay, we have this well, and we have a fixed wellhead pressure. I will tell you just right away where this well came from. We have a reservoir, PR. Okay, so we want to calculate bottom hole equilibrium. And you're going to have nightmares. I come again with equilibrium. You thought that we were over that phase, but no, I come again and tell you equilibrium again. When we make equilibrium, how the curves look like? You have to be able to tell me in the middle of the night. I come first from the boundaries, right, where I have constant pressure, here to here. How do I call that expression? Of the formation, the deliverability of the formation, IPR, co-current, the available pressure at the bottom of the well, called IPR, that's the available. And we know, because it's single phase oil, that it's going to be just a straight line. You just saw it, okay, on Thursday. Now, the curve, when I go now from the other boundary, where I have fixed pressure, from here down, okay, that's the counter current, and that's going to look something like that. Okay, the required pressure, TPR, the required pressure, okay, at the inlet of the tubing at the bottom hole. Where is the intersection? What is the flow equilibrium? The equilibrium flow? The intersection, right? Just like in the case of gas. That's where my system will be operating. So I have first to make the IPR, okay? I said reservoir pressure is 231, and I'm going to make it all the way to 0 to plot IPR. And then I want to calculate TPR. And for TPR, we are going to use this equation that I showed you here, that you won't have to, and this equation probably Dionildo is going to use it very much in his dissertation. Right, Dionildo? Okay, so if you go to Alt F11, we call it P in, okay? That gives you the pressure at the inlet of the pipe. If you provide the pressure at the outlet of the pipe, and you see it's basically the same equation, okay? P out plus, that is the length, okay? The angle. So with this I'm calculating the height. And the angle in here is measured with respect to the horizontal, okay? Be careful. And it should be in degrees. Density, and here I calculate the friction factor times the length, velocity squared, okay? And the velocity I calculate with the rate. Okay. Let's say, so this is a bit more complex function, okay? This function is calling another function inside. Yeah. So let's see the friction factor function. Let's go down. Friction factor requires all the things to calculate the Reynolds and is using Holland. Okay? If velocity is 0, then friction factor is 0. Okay, I have no flow. If I'm in the laminar region, I use the laminar friction factor. If not, I use the equation by Holland. Okay, so that equation, P required, uses that function, friction factor, and then I have P out, P2. That calculates if I give the pressure at the inlet of the pipe, will give you the pressure at the outlet of the pipe. So which equation do we have to use here? P in, right? We want to calculate the required pressure at the inlet of the tubing. And let's see, IPR, it's this equation, okay, one called IPR. There are two IPRs, okay? One giving you pressure. Is that the one we need? Okay, let's go back to our Excel sheet. We have pressure, or we have defined pressure, okay, the range. Now we want to calculate rate. Okay, so we are going to use the second equation, IPRQ. Okay, so let's use first IPR. Okay, here. And that it was called, so we find it here with function. IPR is with IPRQ. Okay? J, I have it here. We have estimated with the formulas that we saw before, and maybe did some tests to verify. Reservoir pressure is here. I block it, and then PWF will be to the left. Okay, as expected for reservoir pressure, the rate is 0, and then I drag it down, and then it's increasing. And if I go to the plot, it shows you exactly what we expected, just a straight line. Okay, no big surprises there. IPR takes J, which is in C2, I have to block it. PR, which is in C1, I have to block it. And E6, which is here, PWF, and that shouldn't be blocked. Now comes the tricky part, the TPR. Which equation do we use? For TPR. Wellhead pressure is 7 bar. They managed to keep it very low, okay, in this field. We will see which field is it. But they managed to keep it very, very low. And we will see why. Why it's very important to keep it low. So wellhead pressure is fixed. We want pressure at the inlet of the tubing. So we have to use the function called P in. Okay, so let's go here, equal, or we call function, user define, P in okay, P in or P out. Be careful. We are going to use P in. And P in requires a bunch of things, okay? First, it requires the rate. Okay, the rate, we are going to use the same rate as for the IPR. ID, that it needs to calculate the Reynolds, okay? And if you see on the friction, you have here also diameter. So the diameter of the tubing is here. I think it's 6-inch tubing. We have to block it. Density of the liquid, it's here. Okay, it's a dead oil, so it doesn't change much along the tubing. I have to block it. The viscosity, that is this number, viscosity of the fluid, and doesn't change much with pressure. Is that value high or low? 0.1 pascals per second. How many centipoise is that? It's 100 centipoise, right? 100 centipoise, is it high or low? It's relatively high, okay? 100 centipoise is like, it's not honey, but it's like very thick. It's starting to get very thick. Normal oil, maybe what you produce here in Mozambique, maybe it has 1.2 centipoise, 1.3, okay? If we have 100, it's 100 times that. So it's going to cause a very high pressure drop. Length of the tubing, length is here. I block it, C3. And then I have to be careful. I have to continue scrolling down. Theta, the angle in degrees, the angle from the horizontal. This well is vertical, okay, tubing angle. So I have 90 degrees. I block it. P out, the pressure at the discharge of the tubing, wellhead pressure, 7. Let's block it. And the roughness is, tubing roughness is here. And then I block it. Okay, and you see the number I'm getting, 212. Does that make sense? Yes? Why yes? It's not any more gas, okay? It's the density. It's the liquid, okay? And if you see the density, it's almost close to water, okay? So every 10 meters of oil, more or less, that gives you 1 bar. And how many meters you have here? 2, 3, 40, okay, meters. So if you divide by 10, that gives you like 234 bar, only in hydrostatic. Of course, we are not exactly 1,000, it's not 1,000 the density, but it's 897, so you get a bit less, 212. But it's a big pressure drop, just by the hydrostatic column, just by the density of the liquid. Okay, and now let's see how it will go up with the rate. Okay, we drag it down. Did you get similar numbers? Yeah. Okay, you see extremely high. When I start to flow, I can go all the way to 300. 100 bar additional pressure drop just due to friction. And that's because this guy is very high. Okay, this viscosity is 100 centipoise. It's extremely high. Now let's see our intersection, how it looks like. Let me take a screenshot of that. Okay, let's see where is the intersection. Where is the intersection? Is here, right? So I'm producing, let's calculate exactly what is the intersection. How did we do that last time? We said we had to create another cell, right? That was PWF minus PWF available minus PWF required. The available is this one. The required is this one. And I have it is exactly here between these two. So let's change this number, right, with solver. We will change this number to drive this one to 0. Okay, let's see if it works. Data solver. I want to drive the difference. I want to drive it to a value of 0 by changing this pressure. Okay, and I obtain that my rate is 1,061 barrels, standard cubic meter per day. Okay, it's exactly this point here. You're changing this number. Okay. So solver, I'm saying drive the difference such that it will be 0 by changing this number here. So now, by looking at the plot, why do you think that these guys put 7 bar at the wellhead? Why do you think? Such a low pressure. Okay, let's try if they use a more normal number. Okay, let's say separator pressure is something between like 800 psi all the way to maybe 2000 psi. No, no, it's 200 psi all the way to maybe 800 psi, and in bar is between 20 or 15 all the way to maybe 50. Okay, so let's say what happens if now you use, instead of 7, if you use 20 bar. Okay, the rate will be much less. Okay, the curve, remember when we change wellhead pressure, the curve is shifted up, so the rate will be even less. So if they wanted to produce something from this reservoir, they had to lower the pressure, wellhead pressure, the minimum pressure as possible. Okay, which is 7. Now I ask you something. What happens if we want to deliver now, let's say, let's say this rate, okay, 2,500 standard cubic meter per day. That's about like 13,000 barrels. Okay, this is an offshore field. That's what I'm going to say at this point. Okay, so a rate of 10,000 barrels is not uncommon. Okay, it's like it's a good producer. If I want to produce with 13,000, can I do it? Not if I don't do any change to the well, right? But what do I have? Because the available pressure is less than the required. So how can I give that energy at the bottom hole to the well, to the fluid? Remember, I have something like that, right? And this is my PWF. Okay, so how do I have, so I have two pressures, right? That they are almost in the same place. Okay, and I want to produce this. So they need to be different. What I do, right, is I put an element that gives energy to the system, which is called an ESP, electric submersible pump. It's like a compressor, but for liquid. Okay, a pump, like a pump you use in your apartment to take the water up to your apartment. Okay, so this ESP, it has to be able to bridge this delta P to provide that rate. And actually, that's what they use in this field. They say we are not happy just with having, if we put here 7, right? We are not happy just with producing 6,000 barrels. We want to produce 13,000, okay, twice as much. And to do that, I have to install a pump in. I have to install a pump in the tube. So let me show you just what is this field. Okay, this field is a field offshore Brazil. It's located, I think it's in this block here, I think. Okay, and it's like that. It's two platforms where you have wells that are deviated. Okay, they are producing from different parts, and it's very heavy. Okay, and it has water injection. So the wells are produced here. You have like a little gas, so you have a separator here, and then the oil is transported to this FPSO, where you separate the gas, and you send it back, and you also separate the water, and you send it back for injection. Okay, and this field is called Peregrino. Let's take we can take a snapshot here. And for this field, because the GOR, the gas is very low, we can use simple phase equations, single phase equations to model the performance. Okay, this is Peregrino. No, in Brazil, offshore. Okay, they use ESPs, and we are going to see now. I'm going to give a short introduction on ESP. ESP, you're supposed to cover it next semester in the advanced production. Okay, but I'm just going to give a short introduction to ESP. So one thing we mentioned here, that this reservoir is producing. It has all of this that you see in blue is an aquifer. And you're injecting in the aquifer, and the aquifer is actually coming into the well. So if you see with time, the profile, okay, the water cut, this is water cut. How do we define the water cut? Water cut is the rate of water divided by the rate of oil plus the rate of water. Okay, that's how we define water cut, and usually in the life of the well is 0 or a very low value, but it starts increasing, and you can get up to numbers. In normal fields is something like maybe 70, okay? If I multiply here by 100, okay, around 70%. But in this field in Colombia, it was like 90%. They were producing up to 95% because it was a land operation. But for offshore, when we reach around 70 or 80% tops, it's already too much oil, too much water that you have to process, okay, that you have to separate. So the oil that you get out of it is not really very much. So for these cases, you can also use, one can also use this Bernoulli equation, okay, the equation that we showed before. And this is like an introduction to multiphase. So how do we work with multiphase flow? One can also use this one, but using average properties. Okay, be careful using average properties. We assume that the oil and the water, when you see them on the side, okay, if you see oil, okay, typically they are like that. One phase will be in like we call it dispersed. Okay, one phase here, water is dispersed. That is, we take a picture of how the flow looks like in the pipe. Okay, so we have two conditions. Okay, one of them is that the oil is continuous. Okay, and this is for water cuts from 0 all the way to 60%, around 60%. You have that distribution. And when you have the opposite, that water is a continuous phase and oil is the one that is in droplets, okay, then you have here the water cut is something between 60 all the way to 100. Which one do you think is better for transport, has less pressure drop? Let's say that the oil has a viscosity of 100 centipoise and water has a viscosity of 1 centipoise. Which one is better?
Second one.
Why?
Both much water.
Has water, but the water is wetting the walls, right? And the friction happens with the walls. If we put here the walls on the side, okay, if you see what causes friction really is the friction, the contact with the wall. So if here we have water, which is a very low viscous fluid, you have less friction drop than if you have oil. Okay, so intuitively we like to be here, but we are going to be during the life of the field through the whole range. Okay, so let's see something. How do we model that with this equation, the same equation? First, they say, well, I have to use density of the mixture. Okay, I cannot use anymore the density of one phase or the other. I have to use the density of the mixture. And this one is density of the water times the water cut, or let's call it, this is the volume fraction, okay, which is Q water divided by Q oil plus Q water. It's almost similar to the water cut, but the water cut is defined with standard conditions rate. Okay, this one is defined with local rates. Okay, plus density of the oil times 1 minus alpha. So that tells you if you have a lot of water, then the density of the mixture is going to be, so if alpha of the water is similar to 1, then the density of the mixture will be very similar to the density of the water. If alpha of the water is similar to 0, density of the mixture will be similar to the oil. Okay? We have to make one more thing, because if you remember, we need density. Density comes in here, right? And comes into the Reynolds. It comes here. And we know how to calculate the density of the mixture. What about the viscosity? Okay, viscosity, sometimes we do the same thing. Okay, so sometimes the density of the mixture is the same using the same expression. Viscosity of the mixture, viscosity of the water, plus viscosity of the oil, 1 minus alpha W. Okay? But, so that expression, how does it look like if we plot it? Okay, density of the mixture. How does it look like if we plot something like that, from 0 to 1? For 0, no water, here we will have viscosity of the oil, right? And for 1, and actually viscosity of the oil is high, so we will have it here, okay? And for 1, we are going to have the viscosity of the water, pure water. So it's a straight line. It's exactly a straight line, like that. Now, tricky enough, that's not how some crudes behave. People came to this equation, they tested it on the field, and they saw something completely different. They saw, actually, that the viscosity of the mixture, it behaves something like that, very crazy. You still have, at 0 and 1, you still have viscosity of the oil and viscosity of the water. But they saw the following. Let me make more space here. They saw that this guy is going to increase up to a point, and then it will decrease sharply down, which is very strange, okay? It didn't match at all that equation. Why, if you have two fluids that have a lower viscosity, why are you going to get a point suddenly that has a very high viscosity, okay? And that's something called, this is called the inversion point. And that happens for some oils, for some oils. And you have to be very careful, because if you design, okay, here if you're going to design your pipeline, okay, let's say you use the worst case scenario, okay, you use the oil, and you say, I'm covered, I'm happy, I'm covered, I covered the worst case possible, like when I'm at the beginning of the field and I'm producing 0, that's the worst. What this tells you is exactly not at all. Okay, if I design with this number, it's a number that can be much higher, and this viscosity can be 2 to 3 times the viscosity of the oil. Okay, very tricky, and it's because if you see on the chart, if you see, okay, this region we had. Okay, we had this configuration, and this region will have this configuration. Okay, and at the inversion point, that's actually what happens. It flips, okay, suddenly. So there is a lot of people doing research on that, trying to find exactly why does it happen, how is it affected, why in some fields it happens and it doesn't happen. But my message is, in those cases, the viscosity of the mixture is viscosity of the oil for this range. So for this range, okay, you use an expression like that, phi with a constant 1 times alpha of water, okay, and for this region here, you use of water times E C1 1 minus alpha 1. Okay, you use some expression, you measure it in the lab, and then you find these coefficients. These are found from lab test, and this model is what is called the Richardson and this is called Richardson. This phenomena is usually called emulsion. So this is the Richardson emulsion model. So my main message here is that when you have oil and water mixtures, you can use this simple equation. You can use it. The main problem is the properties. For density, is just averaging with the volume fraction. Okay? But for viscosity, this works, but you have to be careful with this behavior, okay? Emulsion behavior. So you make some tests in the laboratory, you measure if you have this behavior, and then you find the coefficients that you have to use that are a function of the water fraction. And depending where you are in your field, if you are in an early stage or a late stage, you're going to have a different viscosity. Okay? We're not going to do an exercise on that because we want to do something more difficult, which is multiphase with gas. Okay, with gas you have something similar, but we will see we have a complexity with the density. We cannot just calculate like that, but we have to do something else. Okay, but just to make you aware that if you have mixtures, you can use the same equation. So now let's talk a little bit about ESP. Okay, electric submersible pump. Okay, and this pump, the inventor or the guy that really managed to make it possible was a Russian guy, but I guess he was a good guy, not bad Russian like in the movies. Okay, this guy, even though he had a very serious face. Okay, and I think his name was Armais Plutonov. Okay, not sure if that's how you pronounce it, but he was in Russia and he had the first concept to put a motor submerged, because the pump usually is like that. Okay, you have here you have certain height. The pump, the motor, and everything is going to be. I didn't show here the motor, but yeah, I can show you later. But the motor, what rotates, here you have just a cable, okay? Here you have an opening through the tubing hanger, and you have a line with the cable that goes to the ESP. So you have to have a motor which is submerged. And electricity with liquid, with water, doesn't work very well. So this guy, he was working a long time for that, and he went from Russia, he went from Oklahoma, around the 1930s, okay, and he found a company called Reda. And that's a company that later was acquired by Schlumberger, and you see that name every place. If you're working with ESP, Reda probably came up a few times. Okay, so that's the guy that initially came with a solution, and basically was how to put a motor submerged to make it tight enough such that nothing would come in, and made the technology. Okay, so the pump, how does it work? Yeah, so that's this is actually something we have in our lab. This was a student working with me, and that's how she had oil, which is the red one, and water, which is the white one, and she mixed it in the lab, okay, with a blender. And that's why the viscosity, you see, is higher, because you create a fluid that is very stable. It's like a mayonnaise, okay? When you have oil and water separately, they might behave nicely. You mix it, you put a lot of mixing, a lot of energy, and then you get something like that, which is very difficult to flow. So we were doing some measurements in the lab on the emulsion properties. So an ESP has different parts. Okay, I'm not going to show all of them here, but we have a few parts. Okay, So the last part that we have here is actually the pump. Okay. Then we have that we will see now how, or I can show you right away, I think, how it looks like. Okay, looks something like that. Actually, we can copy these two. Okay. And the pump it's like a centrifugal pump, okay? I guess you have seen before a centrifugal pump. Yes? How it looks like? Okay. So it's basically a centrifugal pump where the fluid goes through the center, okay? Enters, this is flipped, okay? It should be upside down, okay? But the fluid comes through the center, comes through the blades, and then exits on the side, okay? So that's the inlet, and that's the outlet. And you know, in a pump, you have two things. You have the rotor, which gives energy to the fluid by accelerating it. In the rotor, you have acceleration, increased transfer of velocity to the fluid. And then you have diffusion. Okay, you have the recovery. You have two processes, which are acceleration of the fluid, basically increasing V. And then you have the second process, which is pressure recovery. Because if we don't, the energy, we cannot keep it in velocity, because that means that every stage the velocity will be higher and higher and higher. And what does it mean? More friction, okay? More erosion, more problems. So a smart way is say we transfer energy and then we recover to pressure. Transfer energy and then we recover to pressure. And the way to recover to pressure is I just expand, right? Here I have high velocity and low pressure, okay? And then when I come here, I have high pressure and low velocity. And I'm ready for the next stage. So part of the diffusion, the acceleration is made everything on the rotor. The rotor is rotating and accelerating that fluid. And part of it is, if you see this shape, here is small, and then at the end, it has some expansion, okay? But it cannot expand everything. What happens if you try to expand too much in a very short distance? Let's say this configuration versus this configuration. Okay? Here the fluid is a very smooth expansion, so it's able to follow almost exactly nice each channel, right? But when I have this, the fluid, because it's so quick, it cannot follow the channel. So what happens, you have all of these eddies, okay? All of these detachments. The fluid cannot follow the wall. And because of that, you have a lot of energy loss. So in the rotor, we make it very, very smooth, and then the rest we recover in the diffuser. Okay, the diffuser is, yeah, it's not here, but should be, it's here. Okay, so we have impeller, diffuser, and we have a rod that goes through all stages, and it's making them rotate. You see here it has a system. Yeah, maybe I'm going too much in detail into pump, but if you see the axis on the side, okay, it has a small notch. Maybe you know the term in Spanish is called chaveta. So that's the axis. Okay, and you have one element which is something like that, and that allows you to fix it with the rotor. Okay, the rotor is outside. Okay, how do I draw the rotor? Let's, okay, and this is all my rotor. Okay, So my axis has that groove, that hole, where I pass my rotor on it, and then I put that chaveta, I put that key, it's called a key. This is a key. Such that when I rotate my axis on one direction, it will also rotate the impeller. Okay? I don't know if I think I had a figure of that. Let me see. No, I don't have. Okay, so that's how the rotor looks like. Okay, it enters through here, you see, enters through here, up to here, then enters into that channel, rotating, and then comes out. And the axis goes here in the center, is not shown on the figure. We have to, so below that, we have, so below the pump, we have, typically we have the gas liquid separator, gas liquid separator. Okay. Then we have here at some place we have the inlet of the fluid, and then below that we have the motor. And if we paint, we have to pull it up a bit. Okay, we have to paint also, okay, the casing, so just to see where we are. Here we have our casing. And this is something that goes screw into the tubing, okay? Remember the tubing has some joints, so you just screw the pump onto on the tubing. So that's the motor, and the motor here you need this famous cable coming up, okay, from the tubing hanger. So you make a hole in the tubing hanger. I'm going to show you a figure just very quick. Now, I make a hole and I send the cable down all the way to the motor. Okay, and from this motor you have an axis that goes all the way up and rotates the impellers on the pump. Okay, the fluid, the main idea is that the fluid comes through here, okay, comes from the formation and up to here. Okay, and when it passes around the motor, it cools the motor. Otherwise, it will get damaged. So when it flows around, even though it might be very hot, okay, might be 70 degrees or might be 90 degrees, even though it's very hot, the motor is hotter. Okay, it's 100 and something. So you have heat transfer. This fluid is helping to cool the motor. And then here you have that the gas comes out. What color do we use for gas? Let's use for liquid, we are going to use this color, okay, for oil and gas. Okay, and then usually the liquid goes inside through the pump and the gas goes outside and is sometimes produced through the animus. Okay, here I put a valve. Okay, here I have gas production and here I have liquid production. Okay, what else? Let me show you a figure of the what they call the penetrator. This guy, okay, in the tubing hanger. Okay, you see that's the tubing, okay? That's the tubing is screwed into this guy, which is the tubing hanger. All of this structure is called the tubing hanger, and this is the wellhead. Okay, so the tubing hanger, you see this angle here, is sitting on the wellhead, and all the weight of the tubing is just transferred whole by this guy, by this wellhead. And then you have this big hole, okay, it's big, through which you have the cable that goes to the ESP. So you see, it takes quite a lot of space. If you want to increase the diameter here, you don't have much to go. It's not that you have the whole diameter of the casing, okay? It's much less. Okay, so that's the power cable. Let's put here some notes. We're just going to finish. Wait a moment, just stay awake for some more time. Power cable. This is the tubing hanger. And this is the tubing. And I think that's all images I had. Let's see. Oh yeah, so that's another thing. I think it's worth to make the comment that the way we control, so the performance of the pump, it looks something like that. Q, and that's local rate, okay, and versus delta P, it gives you a performance like that. Okay, it's similar to IPR. Okay, and that's for a fixed rotation, RPM. Okay, if I have a fixed RPM. Now, when we did that example, okay, this example here, okay, we said we need this rate, right, with this delta P. So you can come to your plot and you can say required, Q required, okay, with some delta P, okay, and you see you're not going to fall exactly on the line. So for that case, we normally are able to change the frequency of the pump, okay, change the RPM of the pump. Because when we change, let's say we reduce the RPM of the pump, we end up with a graph like that. Okay, just like in a centrifugal pump. So this is F1, F2, F3, F4, where F1 is greater than F2, F3, and F4. Okay, so you're able to adjust exactly when the one that you want is when the curve of the pump passes exactly through that point. Okay. Well, I suggest we stop here, right?
What if the point is above the curve?
Yeah, that we're going to discuss on Monday a little bit. Okay, what happens if the pump is here, or if the point is here, or you see that the pump can fall here, and there are some problems. But we are going to discuss that on Monday. Okay, so today we cover dry gas choke. We are not going to cover any more choke. Okay, for multi-phase, the models are very uncertain. Okay, so it's always better to have measurements. But it behaves in a similar way as for gas. And we talked about liquid. What can we do with the liquid equation? It's very useful, but we have to be careful with emulsions. And we are going to talk a bit more about ESP, how they behave, but we are not going to do any exercise, okay? Because ESP you're supposed to cover in the advanced course. Okay, thank you for coming. Enjoy the weekend and see you on Monday again. Try to rest tomorrow and no. Do you want to have class tomorrow? So